Hello everyone, welcome back to the Genomics Bootcamp. In this video, we will show how to do a parentage control based only on SNP data. So parentage control is, well, indeed a thing that is being done with either SNPs or specialized SNP panels, or also in the past done with microsatellites. This is possible, or the parentage control is possible with the autosomal SNP data that you might have for your individuals. And in this video, we will show how to do this using PLINK. Before we go into that subject, I just wanted to show or talk a little bit about the theoretical background of this. And this is nothing else than the Mendelian rules of inheritance. Now, what we will be doing is checking for so-called Mendelian inconsistencies. According to the Mendelian rules in a diploid organism, the offspring inherits one allele from one parent and the other allele from other parent. Now, we don't know which of the two alleles or which of the two parental alleles it inherits because it's on a 50-50 chance, but we know that one allele comes from one parent and one from the other one. Now, checking on these inconsistencies, we will check on all SNP data that is available. Well, it could be a various number, but well, if you have a like 50 or 60K chip, so it will be all the SNPs and all the autosomal SNPs. We will check, or well, the PLINK will check all the combinations, and we will look for these situations. For example, if the offspring genotype is AA and the parent genotype for the same locus, the same SNP is AB, this is a possible scenario because, well, the offspring got 1A from this parent. But if the offspring genotype is AA and the parent genotype or the supposed parent genotype for the same SNP is BB, this is not possible because one of the B's should have been inherited to the offspring. So this is an inconsistency that is not possible according to the Mendelian rules. So the PLINK will look for these inconsistencies, and if we find many, that will be an indication that in fact the offspring and the candidate parent are not true parent-offspring pairs. This will be what we will see, and well, we will look at the files in detail, but we will have the parent and the offspring with its ID, and there will be an N, so basically a number of mismatches or these Mendelian inconsistencies. And even in the true parent-offspring pairs, because we have so many SNPs that we are checking on, so there will be a few that might appear as inconsistent, but this is a generally a low number, let's say below 20 or below 50. In cases when there is a parent and offspring or a supposed combination, but they are not a true parent and offspring, we will see many more Mendelian inconsistencies. Of course, it will be not all the SNPs, not all the 50,000 SNPs, because, well, some of these might be consistent just by chance, but we will see many that are directly not consistent. So this will be a clear indication that the two individuals here are not parent and offspring. So I prepared two small examples here. This is from pig data, and actually these animals are from the Mangalitsa breed. Well, this data is not open access, so I cannot share it, but I can show how it works on this example. So what we have is the same animal 1, that would be the offspring, and then, well, there is candidate parent 1 and candidate parent 2. And so to make it simple, I also use these as animal IDs. So the animal ID is animal 1 is for the offspring, and the candidate parent 1 and candidate parent 2. This is a standard PET file, and well, I left this first example open because, well, if you remember, so the first column is the family ID, then the individual ID, then the sire, the dam, the sex, and then the phenotype. And in the previous videos, I might have told that we are most of the time not really interested, or it's not really necessary to fill out the sire and the dam, so basically the parent columns. And also most of the time we are okay if we do not have the sex information. Now, in this case, this is not true, and we actually really need to fill it in so we can check for this Mendelian inconsistency situation. Of course, you can do it with updating in PLINK, but for time reasons and so to make it simple, we just do it manually here. So basically what we want to do is assign this candidate parent 1 as the parent of animal 1. And let's say this would be in the sire spot. So it will be the father of animal 1. We save this and we go for PLINK. In PLINK, we use the option --Mendel and --Mendel duos. Well, I think the Mendel works when there are the full triplets, so basically the offspring, sire, and the dam. But if you have only one parent to be checked, and this is also possible, as now we have it in this case that we have only the father. So in that case, you write also Mendel duos. In R, it's a very simple statement. So let's say you have already a quality checked data, and well, we use this pig example. So we set the chromosome set to 18. We use a --autosome to extract only the autosomal markers, and we do this parentage test 1. And we use --Mendel and --Mendel duos for the check on the Mendelian inconsistencies. If you run it in the form as we left it, so basically with the updated parent information, you might get this error. And well, this is right now an expected error, and just wanted to show you so that what happens if you do not have the sex information specified. So in this case, for this particular test, you need to have both the parental information specified and also the sex information for the parent. So we go back to the data, and well, actually what we did is we put the candidate parent 1 in the sire spot. So basically a male animal. So this needs to then be accordingly also sex equal 1. That is the male sex coding. The females would be coded with 2. Now this is done, and well, we can actually fill out or specify also the sex of the offspring, but that is not necessary. And well, we are okay with just specifying the sex of the parent. And of course, this should match the position the parent is in. After running this, now it runs very well, and we see that we have 17 Mendelian errors detected. So this is a relatively low number of inconsistencies based on these 70,000 variants. So this, we are happy with this. And in this case, we say that these two animals are indeed parent and offspring. Now, why we are getting these inconsistencies? They could be some kind of mutations, but also could be, well, just genotyping errors. On our hard disk, we also got a bunch of files that provide us with more information. Many of these files will basically just repeat the information on the 17 mismatches in various forms, but this one is quite interesting. So basically what it does is kind of lists all the inconsistencies. So in which chromosome, what is the SNP name, and what is the actual problem. And we see here so that the genotype of animal 1 is, no, so basically the genotype of the parent is GG, and well, we do not know the mother or the dam in this case, so it's kind of with the stars, but what we know or what we see in the offspring, that is the genotype of this for the same SNP is AA. So this is the situation that I talked about. So this is just not possible based on the Mendelian rules, because one of the G's here should have been inherited. But because overall we have just a fairly small number of these inconsistencies, we still say that basically these two animals are parent and offspring. Now let's run the second parent-offspring pair and see what happens there. So this one I already filled out, but you see that we have a large number of these Mendelian inconsistencies, 2,300 and some more. So basically this is a significantly higher number. So in this case, we say that basically these two individuals, namely animal 1 and candidate parent 2, are not true parent and offspring, so we can actually reject this paternity test. So this was it in short about the paternity testing using SNP data and PLINK. I hope you found this information useful. If so, let me know in the comments, and perhaps we can also extend on this topic. But well, as for now, this was the thing that I wanted to communicate. And so as for now, thank you for your time you spent on this video, and I'd like to wish you a really nice day.